So today I'm going to go through a proof by contradiction exam question. So it's this one here. So let x be a non-zero rational number and let y be an irrational number. Prove that x times y is irrational for 4 marks. Now you may be wondering how on earth I knew how that was a proof by contradiction question. Well, firstly, I've been doing maths obviously longer than you guys and I've seen that question before. So that's how I knew. But let's try and explain why that's going to be a proof by contradiction question. So in maths, we have 5 major methods of proof: induction, counterexample, exhaustion, deduction, contradiction. Now, proof by induction, that is a further maths method. So obviously this question is not going to be proof by induction because you don't need to know induction. And if you do further maths, you still can't use induction here anyway, because you only use induction if you have, for example, sequences of series, limits, sigma notation, so like n equals 1, n equals 2, so on, that kind of stuff. That's where you use induction. Iterations as well. You don't use induction for proofs like these. You can't do. Now, the next method is proof by counterexample. Again, logically, we have to rule out this method. You use proof by counterexample when you can actually come up with a counterexample to prove something. So when you're trying to disprove something, you can offer a counterexample. Or when you're trying to prove that something is not always true, you can obviously offer a counterexample. With this proof here, where we're trying to prove that this is always true, obviously you can't give a counterexample when you're trying to prove something is always true. Again, proof by exhaustion, we can't do that with this example. Why? Because proof by exhaustion is where you exhaust every possibility. So basically, you would be here for the rest of your life picking every single rational number and every single irrational number and timesing them together for the rest of your life. And even on the day that you die, you still would have infinitely many options to go. So we can't use option 3. So the two options that look okay would be deduction and contradiction. I'm going to try and do a deduction proof. So deduction is where you try to mathematically deduce that a statement is true doing algebra. I'm going to try and use that there. And then you'll see why that doesn't really get us anywhere. So let's try and do a proof by deduction here. So I've just written out the question again. So x is rational and it's non-zero and y is irrational. So what can we deduce from these statements? Well, if x is rational, then it means that x must be equal to a fraction of 2 integers. So we'll say that x is equal to n over m, where n and m are both integers. So you remember, use this z notation for integers. And we'll just specify as well that m cannot be equal to 0, because of course you're not allowed to divide by 0 in maths. So we'll just say that m is not allowed to be 0. So therefore, this means that x times y, which is what we're trying to calculate, x times y is equal to n over m, and then times by y. And you can write this as n y over m. So now we need to somehow prove that ny divided by m is irrational. So n is a whole number times by y, which is irrational, and then we're dividing by a whole number. So if we want this to be irrational, we somehow need to explain how this n times y is irrational on the top here, because if that numerator is irrational, then it means the entire fraction is going to be irrational. Now the problem with that is, though it may seem obvious, I mean, if you do a whole number times by root 2, like 10 times root 2, 7 times root 2, or a whole number times pi, 2 times pi, 10 times pi, it seems obvious you're going to get irrational numbers on the numerator there. The only problem with that is, for 4 marks, I don't think we're going to be allowed to say it's obvious that this numerator is irrational. So yeah, we're going to kind of have to do more proof with this numerator, but we're kind of going around in circles, because if that was obvious, then that would mean that this question is obvious. So yeah, this deduction, we're not really getting anywhere with this for a 4-mark question. So really, we've got to do proof by contradiction. So again, I'll just write the same sentences that I wrote here to start with. So let x be rational, let y be irrational. And again, we can write a very similar thing to what we wrote here with the previous proof, that x is equal to n over m. So I'm going to write the same thing again here. Now, with a proof by contradiction question, remember what you have to do. You have to assume that the opposite of the conclusion is true, or the reverse of the conclusion. So you go back to the question, you look at the conclusion. The conclusion is that x, y is irrational. Now, what is the reverse statement, or the kind of contrapositive statement of saying that x times y is irrational? It's that x times y is rational. So to the contrary, assume that x times y is rational. So we're going to assume that x times y is rational. So what does it mean if x times y is rational? Well, very similar to what we talked about with this rational number x. It means that we can write x times y as a fraction of 2 integers. So let's do that now. So again, this means that x times y is equal to some random numbers, whole numbers, a over b, where a and b are integers and where b is non-zero. So now we know that this must be true, assuming this contradictory statement. Now we know from up here that x is equal to n over m. So now we can just plug this in here. So we're going to get n over m times by y is equal to a over b. Now remember, this y is irrational. So what we can do, just rearrange the formula and make y the subject, and let's see what happens. So you're going to times both sides by m and divide both sides by n. So you'll end up with am divided by bn. Now then, a we know is an integer because we said that there. M is an integer, as we said there. B is an integer, as we said here. And n is an integer, as we said here. So what we've got is you've got an integer times another integer divided by an integer times an integer. So obviously, if you do an integer times an integer, you're going to get an integer on the top, and the same on the bottom. You're going to get another integer on the bottom. So you end up with an integer over an integer. And what is the name, the mathematical name for a number that is an integer divided by another integer? It's a rational number. So this here is rational. So you can use this Q notation for rational numbers. And that is a contradiction because y was not supposed to be rational. We assumed that y was irrational. We've gone ahead and shown that y is rational. This is a contradiction. It's a contradiction, and then you just want to write a little sentence at the end of your answer. I haven't really got too much room here. I'll try and write it over here. So you write a little sentence saying, therefore, by contradiction, this original statement back here must be true. So there is your conclusion there. Now, some of you may be again screaming at the screen right now, saying to me, hang on, didn't you just say that it was obvious that an integer times an integer is an integer? Surely that's not obvious. Surely you'd have to prove that an integer times an integer is an integer. Because if I go back to this deduction, this failed deduction, I did say here that this n times y, this integer times an irrational, I said that that was not obvious to prove, but I've gone ahead and I've said that this here is obvious. So why is this obvious? Why is an integer times an integer, why is that obvious? But this thing there is not obvious. So 2 points to this. So point one, you can assume for your A-level maths and also your further maths as well if you do that, a whole number times a whole number is a whole number. You don't need to worry about proving it or explaining it. You can just assume as a primary school fact that two whole numbers added together are whole numbers and two whole numbers multiplied are whole numbers. That's the first point. Now the second point, why can you assume that? Well, because even though you're an A-level maths student and even though you've done years and over a decade of maths education, you actually don't know the real meaning of a whole number. You actually have never sat down and had someone give you a mathematical definition of what an integer is. So because of that, you can't prove results with integers because you guys actually don't even know what an integer is because you've not seen the real definition. So if you want to know like how you prove that a whole number times a whole number is a whole number, you would do that like within the first 2 weeks of a maths degree at university. Yeah, doing maths at university for the first few weeks is a bit of a surreal out-of-body experience. It's like you're going back to primary school and you're doing maths again at primary school, but properly. Like not with primary school teachers, with proper university lecturers who are teaching you the proper mathematical definitions and doing the proper mathematical proofs, such as proving that when you add two whole numbers together, you get a whole number. So it's a bit of a weird experience if you do maths at uni, but you look at that kind of stuff as soon as you arrive.